to love with my eyes closed. I try not to lead with my ego. Everything happened in slow-mo, but we all smiled and said it's alright. Cause you're the one, double the fun, triple the time for love. You're the one, you suck the words from my tongue. That's when I knew I only have eyes for two. I only have eyes for two. I only have eyes for two. Remember we sipped from the same glass. She bit your neck and I like that. We said some things we can't take back. I'm happy it's out in the open. Cause you're the one, double the fun, triple the time for love. Cause you're the one, you suck the words from my tongue. That's when I knew I only have eyes for two. I only have eyes for two. I only have eyes for two. Yeah, I only have
All right, let's get started. Good afternoon, everyone. I'm Matei Ciocârlie from Columbia University. It is my great pleasure to introduce our closing keynote for the conference, Professor Karen Liu from Stanford. Karen did her PhD at University of Washington. She was on the faculty at Georgia Tech before joining Stanford. She has won numerous awards in her career, was a Sloan Fellow, Tech Review 35 under 35, and others, ZGraph, Significant New Researcher Award, and many more. But more importantly than that, I think she has a very important perspective to bring to our conference. Her work is at the intersection of graphics and robotics, which of course share this deep interest in physics-based simulation and generating realistic physics-based motor control. So Karen has been a driving force on simulation, physics simulation, ever since, before it was this indispensable tool that it is in robotics these days. And she has pushed that field forward and has helped bring it into robotics. And also, Karen has a long-standing history of publishing at RSS and engaging with RSS. I distinctly remember RSS 2018 in Cambridge when Karen had 2 papers, and one of them stuck with me to this day. It was a paper about training policies in simulation and doing online system identification at the same time as learning the policy. And this was back in 2018, so it was a paper way ahead of its time. Now, of course, in robotics, that kind of work, simulation-based, learning in sim to real, system identification and policy learning, all these concepts that she was exploring way before anybody else are now so widespread. So I'm very excited about this talk. I've been looking forward to it the whole week. So Karen, please take it away.
Thank you so much. Thank you for the kind words, Matei. It's my great pleasure to be here today to give the closing keynote. So I'm going to start my talk with an observation that probably everybody has heard that by now, but it helps us to set a baseline. Oh, sorry, am I sharing? I am not. Let me go back. There we go. Yeah, so over the past few years, AI has delivered spectacular success, one after another, but they all seem to tell the same story. If we collect enough data, we scale up our models and throw enough compute at the problems, intelligence emerges. And naturally, robotics has reached the same conclusion, right? If we have more data, we will get better policies. So let's start collecting robot data. In just the last few years, we have seen explosion of data collection systems everywhere. Startups are collecting demonstrations. Universities are collecting demonstrations. Companies are paying people to collect demonstrations. But this naturally raises this one question, right? How much data do we need? And you probably have heard Ken Gober has a very, very interesting calculation. Suppose we measure language data set not by the number of tokens, but by how much time it takes one person to read through the entire training data set. And then we can ask how many hours of a robot experience would be comparable to reach LLM level intelligence for robots. And based on the Ken's calculation, the number is 100,000 years. Sounds daunting, but if we can imagine scaling this through parallelism, then we can hire maybe 10,000 volunteers devoting their entire lifetime collecting robot data. And then perhaps we can reach the level the amount of data we want to reach. But notice there is a hidden assumption here. We assume that every demonstration is useful immediately. And this assumption already breaks down on today's tabletop manipulation, and it's going to be a lot harder once we move to humanoids and dexterous hands. So let's look at what happens when we teleoperate humanoids. This is what we have today. The robot can roughly follow the operator's motion, but this works okay with the free-form locomotion. But if you want to do whole body manipulation where precision of any factors is critical, this doesn't work very well. And one thing good about teleoperations, people will always argue that is that you can ask the human operator to close the loop, meaning if there's any errors in your humanoid any factors, you can just ask the operator to adjust, compensate their own hands. But every time we rely on the operator to close the loop, we make this data collection business a little bit harder to scale up. So what we want is a humanoid that understands the intent of the operators and autonomously do the following: maintain balance, reason about contacts, regulate forces, and recover from the mistakes made by the operators. But think about what we just asked our humanoid to do. If we can build this ideal humanoid system, teleoperation system, we have already solved most of the humanoid problems. So yes, collecting robot data in the real world is very challenging. And yes, robotics has a data problem. And this might be the biggest data problem in AI today. But robotics has something else. For decades, our community has been building models, a lot of models. Computer graphics gave us physics simulation, motion priors, digital humans. Computer vision gave us 3D reconstruction, geometry representation, foundation, vision models. Robotics gave us task planners, trajectory optimization, dynamic models. Individually, these models are capable within their own domains. So why aren't they solving the robotics problem already? There are a lot of reasons, and people might say these models are often too narrow to enable generalization. They are designed for solving just part of this perception action loop, and they are built on a lot of simplifying assumptions and often too brittle to deploy directly as policies. And people usually concluded that these models have failed. But I want to suggest a different interpretation here. Maybe we simply assign them the wrong job. Maybe we keep asking these models to become policies, but maybe these models are not supposed to be actors. Maybe they are supposed to just be teachers, and their only job is to give us good demonstrations. And once we view model as a data engines instead of a decision makers, everything changes. Their weakness becomes their strength, and that's what I would like to talk about today. From the perspective of a data engine, these models enjoy many freedoms, I call them freedoms, unavailable to policy. And the first freedom is the access to the privileged information when we use models as an offline data generator. Essentially, I want to ask, can we synthesize useful perception action supervisions purely from simulation? Doing so requires two ingredients to happen. We need to have synthetic world assets. We also need to have synthetic robot behaviors. And each of them has their own challenges. On the real to sim side, creating environments with sufficient realism, diversity, and geometric details at scale has been traditionally prohibitive. On the sim to real side, transferring a policy, training the simulation, and back to the real world has its own challenges as well. However, recent progress suggests that these barriers are beginning to weaken. For example, we now have 3D Gaussian splatting, which can efficiently reconstruct the real world reliably and also efficiently, which gives us a partial solution to the real to sim problem. We also have a whole body motion tracking, which gives us real world robot policies from kinematic motion. And that gives us a partial solution to the sim to real problems. So from this maturing but still fragmented landscape, can we connect these partial solutions into a real to sim to real pipeline for both world assets and also robot behavior synthesis. And I see the missing link here is the data engine that synthesizes pair visual perception and kinematic behaviors. The two boundary conditions here is that the visual perception has to be generated within the 3DGS world, and the kinematic motion has to be trackable by our existing whole body motion tracker. And we call this VLK because it can synthesize unlimited vision, language, and kinematics supervisions. And the key advantage of such a system is the decoupling it enables. We can prescribe the language commands. We can leverage privileged information in the simulators to ease the process of motion synthesis, such as perfect 60 object states or ground truth collision geometry. We can also render corresponding egocentric RGB images after we have the scene and after we generate the motion. So by exploiting targeted annotation, oracle condition motion synthesis, and hindsight rendering, we can scale up this data production by orders of a magnitude to generate complete set of supervisions without any human interventions or human examples. And using this system, we synthesized 48,000 trajectories just in a few hours in this indoor environment reconstructed by 3DGS. So these are all synthetic data. And once we have the synthetic data, we train a policy, a VLK policy, that take as egocentric image, a task instruction in language, and the current robot pose as input, and output a short horizon, whole body kinematic trajectory that can be tracked by existing whole body motion tracking policy. We evaluate VLK policy zero shot, so directly transfer to the real world. And we would train on two different fundamental tasks, navigation and whole body manipulation. So whole body manipulation allows the robot to transport objects to any location commanded by the language. And navigation allows the robot to transport itself to any location commanded by the language. So together, they provide a very solid foundation for many specialized tasks to build on. And here is a long horizon example that includes both navigation and whole body manipulation. The robot is given a language command, and then it will autonomously exercise this whole loop of perception to action cycle, from visual grounding to locomotion to pick up object, transport object, and then put it down. We also create some visual disturbance by adding some disco lights to the scene that was not trained for. And the reason we want to do this is because one important finding of this project is that the policy trained on reconstructed and synthetically rendered scenes can still cross the appearance scene to real gap very well. And the key here is that we need to randomize the lighting condition during training. One key ingredient that enables whole body manipulation is to make contact information front and center. This requires two things to happen. The first is that we need this VLK, this high-level policy, to tell the low-level policy, the low-level motion tracking policy, not only what pose you need to be in, but also which body parts should be ready to brace contact. And the second thing is that we need this low-level policy to know how to utilize this contact information. So how do we train a contact condition motion tracking policy? When we want to pick up the object, it's not just about tracking a pose that puts our hands around the object, right? The hands need to know that it must establish contact so that the contact forces can be exerted. But what contact information does the motion tracking policy need to know, the low-level policy? We argue that the tracking policy only needs to know the contacting body parts, and it doesn't need to know anything about the contacting environments or objects. And this design enables existing motion tracking policy for scene interaction, but we can still keep it as a low-level blind policy without turning it into a vision-based task policy. So we start out with, and this makes the training very simple. You just take existing whole body motion tracking policy, which outputs the PD tracking targets from the current proprioception and the global pose of the robots. And also there's a kinematic command that's come from high-level decision maker. To make a contact condition, we only need to add the contact label as input to explicitly indicate which body length should expect and exploit the contact forces through the interaction with the environment. And we also add a state action history as input to infer the actual contacts with the environment. This way we can make our policy contact aware without explicitly sensing the contact. And during inference, we can use any localization method to provide robust global pose. However, there's still one problem. How do we acquire object geometry, terrain geometry, and the contact annotation for training, right? This is what the training data set. Because most large-scale public motion capture data sets will not give you the the information of the environments. It has a scene-aware motion in there, but you just get the human motion, not the environment. So we need to address this data bottleneck by coming up with a new method. We call it hindsight reconstruction of scene. Specifically, given a retargeted robot motion, we infer scene interaction graph that identifies which body lengths should contact the terrains or movable objects over time, and then we reconstruct the continuous geometry the best we can to explain the motion. And this turns an ordinary human motion capture data set into a contact-rich robot scene interaction data set suitable for training. And this is data set is also public released. So here we show that our contact condition policy, a single tracking policy, can perform various scene interaction, including terrain traversal, sitting on a chair, and stepping over the obstacles, as well as whole body manipulation and whole body manipulation together with the terrain traversal. So everything we're doing here is one single policy that can interact with the scenes. It's also important to show that the contact condition policy does not regress when we just ask it to track a normal motion on a flat terrain. Okay. All right, so that's freedom number one. Freedom number two, using model as a data engine gives us unlimited data coverage for state space and action space. And let's look at one example in dexterous manipulation. Manipulating articulated tools is actually quite common in our daily life, right? When you want to use a tongue to serve food or use pliers to cut wire. And at the beginning, it feels like it's just an extension, a trivial extension of pick and place task. But it's actually deceptively hard. And I love to explain why this is the case. So let's look at this physics puzzle, my favorite thing. Suppose you want to squeeze this tongue using 2 fingers. Which pair of contact forces is better for this task? The blue pair or the red pair? The answer is actually not obvious, because on one hand, the red pair is better for stabilizing the whole system because the net force is 0. But notice that the force is not aligned with the normal of the surface of the tool, which means that your fingers can slip easily. On the other hand, the blue pair is good for tool actuation because it can generate most effective torque against the spring force. But the non-zero net force destabilizes the system. So not obvious. Now let's look at the profile of this tongue. Oftentimes, our hand is not exactly where the center of mass of the object is. If we use 2 fingers to hold the tongue, we can lift it through friction and against the gravity, but at the same time, we're generating a torque, right? And that gives us an undesired rotation. So we need a 3rd finger to counteract that rotation. So at this point, any tiny little change of any finger is going to offset this very delicate balance. And finally, generate such a force depends on contact points and joint configurations. Through this nonlinear Jacobian equation, if we change the contact location slightly or the joint configuration slightly, this might drastically change the amount of action needed to generate that force. So I wish I could say we can just use imitation learning or reinforcement learning to solve the problem. We tried, and we tried with our best to put together a teleoperation system, and we conclude very quickly it's impossible, almost impossible to get any data because the operator simply can't be efficient in the face of all these micro contact dynamics. And reinforcement learning is also hard, right? Because this is long horizon going through many different phases, from picking up a flat object on the lying flat on the surface to forming a functional grasp to actuating the tools to actually use the tools to manipulate objects. So using a sparse reward at the end of this long horizon is going to make training really difficult. And it's almost equivalently hard to design a dense reward that captures all these complex micro contact dynamics. But there's someone who can solve the problem, the animator. The animator can do anything. They can come up with any motion sequence in thin air using some 19th century technique called keyframe animations in a coarse-to-fine fashion. So given a scene, the animator will first design the keyframes to indicate the key events of the animation, and then they interpolate the keyframes into a trajectory they call it in-between frames. That's great, but we need not just one sequence, we need a lot of them, right? We need to generate animation at scale for robot learning. So if the data pipeline is slow and demands a lot of expertise, this is still not good. But we found that, unlike animations, we don't need to generate a continuous long horizon sequence one after one. Instead, we can generate many short motion clips that depicts only a portion of that task. And once we have enough of these short motion clips, machine learning will figure out how to put them together. This finding is crucial because it allows keyframe to be generated in batches with an autonomous or automatic procedure. And we can then connect these keyframes randomly by generating short motion clips to densely cover the state space. And breaking down this long sequence also allows us to use heterogeneous methods to generate motion for different parts of the task. So some part of the motion, some part of the task, it requires very delicate physics, then we use RL. Some parts that need to anticipate the future, then we use motion planning. And some part is good with just old-fashioned kinematics, then we just use spline interpolation. Right? Besides being able to animate efficiently at large scale, we also need the keyframes and in-between frames to be dynamically plausible and diverse. To achieve this, we employed existing work called lightning grasp, which give us an unlimited, diverse, feasible grasp. We also scale up RL training to generate many dynamically challenging but short horizon motion clips. RL can do a pretty good job at that. So at this point, we have a data soup, and how do we get that? We employed at least 4 or 5 models I talk about, right? All these methods, you know that, everybody knows that, but when you put them together, they become something very powerful. And once we have a dense corpus of motion clips, that's when we start using learning. We can simply apply imitation learning to connect these motion clips into policy. And since the data is generated in simulation, we use point cloud as the vision representation. At the deployment, we utilize another existing model, or another 2 existing models, to convert RGB into the point cloud. So here we show a perceptive policy performing a long horizon task of picking up a tongue and manipulating it to serve food. Here on the right, we show another type of articulated tools, a syringe. The actuation mechanism is very different for syringe, and in order to push out the water, you actually need to use a significant amount of force, and that makes the whole task even more challenging. So you probably notice that many of these tools are very small and flat, and comparing to our bulky hand. So a flat tool lying flat on the flat surface, just picking it up is very challenging. And I start to realize why most of the demos I've seen, the object is always propping up, like you can just grasp. Now I know why. All right, freedom number 3, when using model as data engines, we don't need to apologize to anyone that your model is not generalized enough, because the purpose of the model is to provide good demonstration like a teacher. And if you want to train a generalist that can perform many, many skills like a parkour athlete, just use more specialized models. This is a paper we presented at RSS this year, so I will be very brief. The idea is to train many specialized teacher policies, each of which can only do one parkour skill. But when we pull these specialists together, we have a wide variety of trajectory to supervise a generalist student policy. Here, all these behaviors you're seeing is generated from onboard perception, and we use a simple velocity commands to steer it, and we don't need any of the reference motion to track. And this is the reason that we can also just change the environment on the fly. Here we enter this parkour course and move the objects around, and you can see the policy can adapt to that autonomously using its own onboard sensing. Okay, freedom number 4. We can exploit hindsight during data generation. I already talked about hindsight twice already, right? Being useful for hindsight rendering, and we can use hindsight for geometry construction. I want to add another interesting way to use hindsight. I call it hindsight physics. And I will use compliance control for humanoid robot as an example. We want to be able to control not just the movement of the humanoids, but also how stiff the humanoids move. And this is important when there is a forceful perturbation during the interaction with the environments or with another person. Suppose we are training a policy to track the goal positions G of some any factors. We typically use a simple tracking reward like this. To incorporate compliance response due to perturbation, a popular idea is to directly modify the reference motion to reflect the perturbation, and then train a policy that tracks this modified reference motion. In this way, the policy learns that, oh, if I infer there is a perturbation from the state action history that's given to my policy, I would be rewarded by tracking the goal that is not G, but a modified version of it. All right? So that's why the policy learns. But this approach requires someone to modify the reference trajectory. If your reference trajectory is simple, like standing still, creating a perturbed version of that is not hard. But if your reference motion is running or doing parkour, how do you modify that so it looks like a perturbed version of a parkour? Simple IK process is not going to give you a natural perturbed motion, and we end up destroying this nice distribution of a human reference motion from our mocap data. So our key insight here is that a reference motion can be reinterpreted in hindsight as the resulting response to some external perturbation. So instead of modifying the reference trajectory, we modify only the conditions provided to the policy as the goal. This goal is modified by subtracting the effect of the perturbation, and we call it hindsight goal. For the reward, we simply track the original reference motion. So now the robot learns that when I infer there's a perturbation through my history, I shouldn't be tracking this hindsight goal, and instead I should be tracking this original reference motion. This will give us exactly the behavior we want. The robot yields compliantly to the perturbation while remaining within the distribution of the high quality reference motions. So during training, we first compute hindsight tracking goals under randomly sampled perturbation F and randomly sampled stiffness K. And we also train the default case where F is 0. It's just like a simple, simply a normal motion tracking procedure. Step 2, we train an RL policy conditioned on the hindsight goal, but rewarded by tracking the original motion. This policy is also conditioned on commanded compliance. So we give a high-level decision maker a knob to tune to decide how stiffness they want the policy tracker to be. And similar to the contact condition policy I talked about earlier, we don't need the policy to be force aware. Therefore, we don't need any additional sensors or tactile sensors. Instead, we provide the history of state action to the policy and the ground truth force, applied force to the critic. So the policy now has a chance to learn how to infer ground truth force from its own history. And at inference, we remove the critic and use a high-level planner to provide a desired goal. Know that the goal is not a hindsight goal anymore. This is the actual goal we want the robot to achieve. Here we show that the humanoid is able to use different stiffness for different hands. The left hand is stiffly holding the whiteboard, while the right hand is more compliantly wiping off the letters. And being able to control the stiffness of the humanoid is really crucial because we want our policy that can be stiff when the task requires it and be compliant when safety demands it. And this one single policy allows us to have a very detailed control of the stiffness. So all these freedoms allow the models to synthesize the best supervisions possible. Once the policy trained on synthesized supervision becomes sufficiently general, we can continue to improve it and collecting more data to fine-tune it. The hope is that we will eventually reach the foundation model level policy. So this is definitely a legit approach, and a lot of people are pursuing that, but I want to explore an alternative route. How do we improve the policy without collecting any new data? This way, we can truly view model as a flywheel. Once it starts turning, it will just keep going on its own. I will illustrate how the model flywheel improves two different axes of the policy. The first example shows how we repurpose the old data through model-based methods to enable cross-embodiments without collecting any data from the new embodiment. And the second one shows how we can utilize old policy to further explore the space in order to improve its capabilities. Given how much we invest as a community, we invested on data collection, I really hope that, I really want to believe that all those efforts can work across robot platforms. So previous research has demonstrated some cross-embodiment capabilities over different types of arms and different types of grippers, but the differences is honestly not that big. Cross-embodiment would be much more meaningful if we can cross the gap between grippers and human-like hands, like dexterous hands. And this is a very practical and timely problem because the community has amassed enormous amount of gripper data, while the frontier is arguably shifting towards dexterous hands. Can we repurpose the gripper data and models for dexterous hands? That's the question I want to understand. So in this project, we show that we can make it happen through pure model-based methods, no learning. Given a pre-trained VLA, such as this OpenPy05 trained on the Droid data set, our goal is to deploy this policy on a target embodiment never seen before, such as this dexterous hand, without collecting any dexterous hand data. And reaching this zero-shot transfer on a new embodiment is challenging because there is the kinematic gap, there's also this visual gap. The kinematic mismatch can be somewhat overcome with a geometric solution. Suppose we do the simplest possible thing. We retarget the fingertips of the gripper to the dexterous hand. So the gripper policy can now drive this dexterous hand. But the visual gap, which is the end-effector appearance in its own wrist camera view, is a lot more problematic. So the project is actually focusing on the visual gap. If we close the kinematic gap using that simple IK I talked about and leave this visual gap open, this is what happened. At first, it seems like it's working, but a task after another, it breaks. And this is because the perception stack trained on a gripper bakes its appearance into features. So if there's anything that looks different during inference, the VLA is going to OOD. Our solution is simple. Instead of fighting this visual gap, we remove it, both in training and during inference. Masking or in painting visual appearance of the robot has been explored previously for co-training with cross-embodiment data, and we found that it's very effective for transferring gripper policy to a dexterous hand, zero shot. Specifically, we use the camera parameters and the current state of the robot to render a mask that covers the end-effector from its own wrist view. And we also augment this mask so that the VLA is not going to overfit to its own this particular silhouette. Now, instead of modifying the pixels on the images, we use the augmented mask to compute an attention mask for the vision encoder. And this way, we can hide the source embodiment inside of a VLA. When deploying on an unseen target like this embodiment, dexterous hand, we hide the target and effector the same way. And during deployment, we do not need to augment the mask. But still, we don't modify the pixels. We modify the attention masks. Now, we also need to close the kinematic gap during deployment. To convert from the source action to the target action, we use 4 kinematics followed by inverse kinematics to turn this into the action space of the dexterous hand. There is still one loose end that will cause this VLA to OOD, which is the input perception, proprioception as input to the VLA. We need to convert the dexterous hand state to the gripper state, again, through FK-IK operation. No learning. We evaluate on 4 embodiments: the gripper we train on, an unseen UMI gripper, and a 5-finger dexterous hand. We use Sharpa hand, and a different robot arms and gripper. We use YAM. And now we compare with the 2 different baselines. The first baseline retargets the action, but never hides the body. So its wrist view stays out of the distribution. It doesn't work. The second baseline, lab, aligns the embodiments at the language layer, which gives us a cleaner, more accurate action interface, but it still cannot close the vision gap. And our method can place and grasp cleanly. Closing, the reason is because we close the vision gap, and that's the reason that zero-shot transfer works. The same pattern holds on the unseen UMI gripper. Here, we tested it on a folding towel task. Our method is the only one that can complete the task. Again, it's closing the vision gap that matters. The same pattern holds for the YAM on this marker removal task. So our method turns this data collected in a single gripper into a body-agnostic foundation. We didn't use any new dexterous hand data. We didn't train a new RL policy for dexterous hand. Instead, we use model-based methods to rewire an existing gripper policy to work for dexterous hand. and make dexterous hand instantly as good as the gripper policy we have today. But honestly, making the dexterous hand to mimic gripper's behavior definitely is not the best way to utilize the dexterity that this hand can provide. But the way we see it, this is that we see this as policy as a strong initial point. We can then fine-tune it to be more dexterous from there. And the real message of this work is that hardware can keep changing, and they will, but the data we have already collected does not have to be left behind. In the second example, we are interested in precise assembly using dexterous hand. And just like articulate tool use I talked about earlier, the challenge of precise assembly is beyond today's capability of imitation learning and reinforcement learning. The contact-rich nature make teleoperation very difficult, and this task is also sparse reward, right? The reward is usually given at the end if your par reaches the final pose or not. So RL is also difficult. Intuitively, before learning the hard problems of perfecting precise assembly, we should be looking at the easier problems of maybe playing in the free space. And this is a classic pre-training, fine-tuning paradigm that's been popularized in the last few years in our community. The process of fine-tuning can be defined precisely because usually we know exactly what the final task should look like. But the recipe for pre-training is somewhat more elusive and less understood. So how do we define this play pre-training so later it can help training the precise assembly? Playing is a general capability without a specific goal in mind. And if you put it into the context of object manipulation, it's reasonable to think about playing is like moving random object around to a random location into a random orientation. And this can be achieved by making the RL learning environment as general as possible in terms of the object we learn from and in terms of the distribution we use to sample the initial and goal poses. This is a work that we published at RSS this year. It's called Synctorial. With the play pre-training, we are able to fine-tune the policy to achieve precise assembly tasks within a few hours of a training, shown as the blue curves. And in contrast, if we train the assembly task from scratch, whether we have dense reward or not, the learning never took off, shown as the orange and gray curves. So here is the deployment of our fine-tuned policy zero shot to the real-world platform. It is able to achieve the precise assembly task, the long horizon tasks, and it can utilize pickup, in-hand manipulation, insertion tasks, all in one policy. And here we show tight insertion task, which requires sub-millimeter accuracy. So yes, pre-training is necessary for learning precise assembly, but is fine-tuning necessary? Since our Synctorial policy is pretty general, maybe it can just be used for assembly task. The answer is no. If you just have pre-trained policy, it might be able to bring the parts to the neighborhood of the goal, but it is never precise enough to reach sub-millimeter precision required by the assembly task. To do so, we still need both pre-training and fine-tuning. And what's interesting to see here is that the policy is not just being more precise. It actually learns a strategy to first feel where the hole is, and then push followed by the insertion task. So learning from play has been explored previously by a lot of other people, but it is unclear what aspect of the play pre-training recipe matters for the downstream fine-tuning. So we want to take the opportunity of this project to answer that questions. to study the design choice that make play useful for precise assembly task. So we asked the following questions. Does object diversity matter? It turned out that increasing the number of objects you train improves the policy quality, but with a diminishing return at around 100 objects. What training objective in the reward function matters the most? And it turned out that the orientation accuracy reward is super critical. If you just have the translation reward, translation accuracy reward, your policy never learns the in-hand orientation that's required for the assembly task. Does trajectory diversity matters? Yes, learning from random trajectory is really critical because we want a really broad coverage of goal poses in our pre-training. Does the pre-train policy need to be precise? Yes, to some extent. If we train a policy that can reach 10 centimeter accuracy, that's useless for assembly. But if you lower that threshold to 1 centimeter, that becomes more effective. In general, all these design choices emphasize learning in-hand manipulation using fingers instead of moving around with a fixed pose. Here we show 15 different rollouts from different initial poses, and all the videos are shown in 1x speed. And finally, we discovered that the play pre-training is also great for learning to recover from mistakes. It's very encouraging to see that this kind of emergent intelligence can be transferred from pre-training to fine-tuning policy. All right, in the last few minutes, I want to pop one level up. If we can use model as data engine to train policy and then bootstrap the learning without more data, that is a pretty powerful paradigm for robot learning on its own. But is this how we reach human-level skills? Decades of research describe human skill learning as a progression through 3 stages. Cognitive stage, where we focus on explicit model-based reasoning. Associative stage, where we improve our skills through practice and experiences. And autonomous stage, where we learn to reuse and compose learned skills to solve new tasks and new, more challenging tasks. So I think the robot learning pipeline we talked about so far resonates well with the first 2 stages. Cognitive stage, because we use models to generate experiences. Associative stage, that's where we distill experiences to policy. But to get to the last stage, autonomous stage, where we can reuse and compose the learned skills, I don't know if the answer is the final arrival of robot foundation model. Given the fast progression of robotics and AI in just the last few months, I say months, not years, the future, the way I see, is probably not going to be a monolithic robot foundation model as many people believe a year or 2 ago. Instead, it might look more like a compositional ecosystem of specialized models coordinated by increasingly more capable orchestrators. And this might remind you what Ken Gober has said once.
I want to make an argument here today about good old-fashioned engineering and why it's still valuable.
This modular design has been around for centuries, but in the era of AI, a lot of people lost faith in that. That's understandable because up to this point, we haven't seen a model that is operating at the skill level we want, and we have not seen orchestrator that can be smart enough to come up with creative solutions to utilize the models. But both barriers are beginning to disappear. In the next few months, and I say months, not years, we will see more and more powerful orchestrator that knows how to put together those tools and models together for challenging tasks autonomously. And this entire robotics community, inspired by the vision of robot foundation model, is churning out a more and more capable policy at the very fast pace. Ironically, foundation model is in fact accelerating this vision of good old-fashioned modular design. So the last freedom I will offer in this talk is start with the models, generate data, use your data to train policy, continue to improve it iteratively, but stop whenever. Intelligence doesn't need every model to become universal or foundational. A model only needs to be reliable and useful within its interpretable assumptions to earn its place in the ecosystem. With that, I'd like to thank you for listening, and thanks all my collaborators and funding agencies, as well as industrial partners. Thank you.
All right, thank you, Karen. We have ample time for questions. That's a huge opportunity, so make use of it, please. Let's start right here.
Hi. In the example where you transfer a two-finger grouper policy directly to a dexterous hand and different morphologies, I was wondering, are you mapping, in the position mapping, are you mapping the key points of where the gripper is making contact to the dexterous hand directly?
Yeah, so we're mapping the fingertip of the grippers, and then we ask the dexterous hands to follow those two fingertips in its own space.
I see. So if it's just mapping the two-finger endpoints where it's making contact, I was wondering how the dexterous hand is like closing all fingers to grasp the object.
Right. So, so the dexterous hand is driven by IK. Right, so IK will actually come up with a pose to close that. We don't have a direct control over other fingers, but as I said, we see this as a starting point for that policy. So now we have a dexterous hand policy that can do things as good as the grippers. Probably not the best way the dexterous hand should be used, but starting this as the initial policy, we can fine tune on it.
I see. One more question is, instead of masking out the gripper entirely from the image, what if we retain those key points that you're actually mapping, in position mapping, right? So just retain those key points as like, some colored bubble or something that it can actually map to the final policy.
Yeah, so that could help. We actually tried that. We didn't see it help too much. But the key is that you still have to mask your own appearance to avoid OOD.
Yeah. Okay, thank you.
All right, let's move to the other side.
Thank you so much for the talk. The last part that you kind of scratched the foundation models and go to the modular thing was kind of interesting and a bit shocking to me. So like I always want to think about going from this, core simtorial, dexterous, multi-finger, like how to basically embed those skills into large foundation model so that you can sort of text condition to get any, nice multi-finger behaviors out of VLA. But I was almost like told that from you that don't do it, just go with modular thing. So like, do you think like we don't need to like go towards this, large VLA that does everything? Or?
Yeah, so first of all, I'm not against data, right? So the first image, it's not shown here. The first thing I said is that we use models to collect data, right? So, let's just say we get our models, we get our dexterous hand to be able to do the things that gripper could do. That's a great opportunity to start collecting the data, right? And then you can use that to train an even better dexterous hand policy from there.
Okay. But I guess like going from this multi-finger in-hand manipulation tasks and sort of embedding that capability to like a general purpose model, like how do you bridge that part with this modular approach?
Yeah, so I don't know I would call it modular approach, but it is if you think this is a starting point, and then the next thing you would do you can start with the RL, for example. In a way, you can combine this project with the next project, the Scene to Real project, right? So this is your starting point, and you can fine tune it. You can say, these are the points that's important. This is almost like the affordance you need to know. And we learn the affordance from the gripper policy, and from there, you can actually explore other ways to pick up things using your multi-fingers. So that's the way I think it as a starting point, right? Like that you learn the mapping between what you see and what the affordance is. And that is actually the hardest thing to learn just in RL, right? And then after that, you can use your RL in the simulated environment to figure out how do you position your fingers, how do you utilize the context to pick up the objects in a better way.
Thank you so much.
Okay, let's stay on that side. Jeanette?
Thanks, Mate. Hi, Karen. Nice talk.
Thanks.
I have one question also about that shocking last part that you presented.
Shocking.
I'm actually wondering what you think about the interfaces, because to me, putting together these modules didn't fail necessarily because the modules are not good enough yet, but more about what the assumptions are that each module makes about what the other module provides as an input. And so if you have this orchestrator, yes, it could figure out like how to put everything together or what the input and the output of each should be, but I feel it should also maybe look at the interface itself. So I'm curious what your perspective is on this and what do you think it will come up with?
Yeah, I think that's a really good point. That's one thing I mentioned maybe in passing is that it needs to operate, the model has to operate within a interpretable assumptions. And that's probably address that interface you're talking about. Every model, we know how to use it. It's very clear what the input output is. And the way I think it is that if I can ask an animator to use those tools to come up with something, or a PhD student to come up with something, then probably our orchestrator in the near future can do that too. So if models are useful enough for humans to figure out how to put them together, then I am optimistic that this can be done autonomously in the future.
Okay.
You don't believe me?
Yeah, I'm thinking like, wait, but
Yeah.
if people haven't figured it out, then I don't know if that thing that is trained on human data can figure it out, right? I think there has to be some other innovation on the interface somehow. I'm not quite sure what it's going to be like.
Yeah, the better interface will definitely help the agentic part to figure out more easily.
All right, coming back on this side, and I think we have time for one more question.
Hi, thank you for the excellent talk. My question is also about the last slide, which is your future vision. The modularized robotics is where each module is right now it's like a new paper per module, but in the future, do you think we could have robots that could learn its own new skills and modules on its own, and would that be the next abstraction after? And do you have a guess on how we can achieve that the robot can learn its own new next modules on its own without having us having new papers to have new modules?
Yeah, that would be wonderful. I think the one thing I can imagine this can roll out is that the orchestrator will discover the weakness of this model ecosystem and suggest what missing model that needs to be learned. And that's probably one possible way to achieve what you envision.
And unfortunately, I think we have to stop here, so please catch Karen during the last poster session for more questions, but let's thank her one more time.
Thank you.
And with that, we are ready for the final oral sessions of the conference.
All right, folks, welcome to the second to last paper session of the conference. We'll be your co-chairs. I'm Jake Weldy from Cornell University.
I'm Fan Shi from National University of Singapore.
We'll be chairing your session on robot and sensor design. So let's get started with the first paper, which is Craft, a tendon-driven hand with hybrid hard-soft compliance, which will be presented by Leo Lin and Jay Moon.
Okay, hello. We're introducing Craft, the tendon-driven hand with hybrid hard-soft compliance for contact-rich manipulation. I'm Leo.
And I'm Jay.
Inserting and twisting a key requires compliance because the key and the keyhole are never perfectly aligned. Compliance means that the finger is rigid enough to maintain its shape, but also soft enough to deform when needed. During key insertion, compliance lets the key shift so it does not jam, and during twisting, compliance reduces the twisting force on the key.
Towards this end, we introduced Craft Hand, a tendon-driven anthropomorphic hand. Our hybrid finger structure places rigid PLA on the outside for structural alignment and TPU joints on the inside for elastic deformation. And the metal dowel pins holds the structure. Using hard and soft materials, we have the first joint, the dip joint, and the second joint, the pip joint. Craft utilizes a rolling contact joint where the two curved surfaces roll against each other instead of rotating around a fixed axis, which it differentiates from a conventional rigid pin joint. Craft also utilizes a crossbelt mechanism, so the dip and pip joint can both bend equally and simultaneously. In the simplified diagram, if the left side moves down, it will cause the right side to move as well, and that is because of the fixed length of the orange line and the blue line. And that is the less simplified model. So using these design principles, our finger can absorb impact without needing a complex back-driving control.
Next, to teleoperate the hand, we use Frank mocap to extract body pose in order to control the robot end effector, and we use hammer to extract finger joint angles in order to control our robot hand. We highlight one task from the teleoperation experiment, picking up a delicate raspberry. Leap hand, a rigid hand, struggled with this task as it crushed the object easily. Our hand, however, not only took only half the amount of time to align, but also did not crush any of the objects during our experiments. Our hand can pick up rigid objects such as medicine pills, tennis balls, as well as toy broccolis, for example. We can also insert things like inserting plugs, USB sticks, and finally, as previously mentioned, inserting and twisting a key. These insertion tasks are much more hard to complete with the more common rigid hands. We can do soft objects like picking up toast, wiping whiteboards with sponges, as well as picking up paper cups. We can also pick up plush toys, and next picking up fruits, and finally picking up wine glasses. These teleop videos are all at 1x speed. So we highlight the hand covering all 33 grasps from the popular Felix taxonomy, further showcasing its flexibility and how closely it models human hands. This is a Craft hand bundle. We don't make any money off this, but it's just a convenient link to get all the motors for this open source project. For more details, you guys can come to our poster session. Thank you.
Thanks, folks. Our next speaker will be Changyi Lin, who will present LightTact, a visual tactile fingertip sensor for deformation-independent contact sensing. Go ahead.
Okay. Hi, everyone. I will present LightTact, a visual tactile fingertip sensor for deformation-independent contact sensing. So to sense physical contact, many existing camera-based tactile sensors follow such a pipeline. The physical contact force deforms the tactile sensor, and then the camera absorbs the deformation as the tactile signal. This has been very successful And so, for example, the geoscience and light detection sensor, they can accurately reconstruct the geometry. But this also means that the signal depends on whether the contact can produce enough visible deformation. However, many manipulation tasks involve light contact interactions. For example, when we touch water, touch cream, or gently hold an object like tofu, the soft object, the physical contact already happens, but it doesn't produce enough deformation, or it produces invisible deformation. So can we sense contact without relying on visible deformation? And on the sensor surface, there are non-contact areas and contact areas. So LightTech achieves this. On the camera image, the pixels corresponding to the non-contact areas remain near black, while the contact pixels can capture the visual appearance. We achieve this by putting the camera on the side of the transparent silicon, so the external light cannot arrive at the camera because of refraction and TIR, while the contact light can pass the vertical surface and can arrive at the camera. And then let's see some demo. Okay, so on the left is the tactile sensor. And then there are raw image and contact segmentation image. So this sensor can sense light contact. We can see the objects are deformable or even liquid. And with the sensor, the robot can also spray the water. It can detect the contact with the liquid. And also, it can enable the robot to interact with the soft film. And finally, we have open sourced the sensor, including hardware, software, and tutorial. And I also have several tactile sensors available to give away. So if you are interested, please come to my poster. Thank you.
Thanks, Changyi. Our next speaker will be Jingyi Chen, who will be talking about bridging language and physics, automated design of continuum robots with large language models.
Hello, I'm Jingyi Chen, and I'm glad to share our work about how we use LLMs for automatical design of robots. Automating robot design has long been a challenging problem. Some recent work tried to take advantage of LLM, but language models often fail to understand the physical cause of the robot performance. Our insight is that to bridge the gap between natural language and 3D simulation, the LLM needs better access to the physical behavior of its own designs. Based on this idea, we propose our agentic framework. The process begins with a task objective description and a Mujoko XML file of the environment. After the initial design from the coder agent, the output enters a hybrid refinement loop. First, a physical stability validator loads and tests the model in simulation. It detects syntax errors, ineffective actuation, self-collision, and other abnormal behavior, then returns structured feedback to the coder. If the design passes the validator, then a scene integrator places the robot into the environment. An LLM judge checks whether the complete design follows the intended design space and is structurally coherent. Finally, A human engineer may optionally provide high-level feedback. Designs that pass the loop are sent to a downstream reinforcement learning pipeline for functional evaluation. To evaluate the framework, we choose tendon-driven continuum robots with segmented backbones, which has high degree of freedom and complex contact behavior, while remaining practical for simulation in MuJoCo. We reviewed soft robot-related works and designed a benchmark of 14 tasks across 4 categories. As a result, our framework achieves a 96% rate of passing the simulation feasibility check. Then, after common reinforcement learning, 26% of the generated robots successfully complete their assigned task. We also perform ablation studies on the framework modules and on different LLMs. To make the process easier to inspect, we develop a web-based interface. Users can configure the task and environment, monitor agent logs and the live MuJoCo scene, inspect the generated XML, and provide natural language feedback for another refinement round. Here are several designs generated by GPT-5. Their morphologies are created automatically, while the motions shown here are learned through reinforcement learning. As LLMs improve, we hope that the framework will produce increasingly useful and inspiring designs for robot engineers. To demonstrate real-world feasibility, we fabricate 3 representative robot designs and test them on the same tasks in hardware. In summary, we present a framework that bridges language and physics for automated robot design. We hope this work can serve as a step toward more capable auto-design systems in the future. Thank you for watching.
Thank you, Jingyi. Our next talk will be by Kei Ikamura, speaking about latent diffeomorphic co-design of end effectors for deformable and fragile object manipulation.
Hi, it is my honor today to talk about our work on co-designing end effectors for deformable and fragile object manipulation. The joint optimization of robot morphology and control, also called co-design, has been studied extensively for rigid and articulated manipulation. For deformable and fragile objects, however, it remains relatively unexplored. This is precisely the regime where morphology is most consequential. An unsuitable contact geometry does not merely reduce success, it compromises object's integrity too. So to bridge this gap, we formulate a stress-aware co-design problem. Our goal is to jointly optimize the 3D shape of end effector fingers alongside their control strategies. Our objective trades off 2 terms, maximizing task success while minimizing the object's internal stress experienced. Now, to parameterize our finger geometry, it is crucial to ensure the generated shapes are diverse and remain physically valid. For this, we use diffeomorphic deformation. Specifically, we parameterize a stationary velocity field using radial basis functions to smoothly deform a base mesh. On the left, we show an illustration in 2 dimensions. Here we also show some examples of the fingers generated with the formulation, shown as the blue mesh. Now the raw shape parameterization is approximately 7T-dimensional, which is compact but still challenging for black box optimization. So we apply PCA to a set of manual designs to obtain a compact latent space of 15 dimensions. Our optimization pipeline operates in a bi-level structure. The outer loop searches the latent design space using CMAES, while in the inner loop, we utilize an adaptive model-based control strategy. By leveraging privileged simulator signals like soft body stress and centroid motion, we optimized for pre-contact poses and trigger manipulation phase transitions. This bypasses the severe sample inefficiency typical of reinforcement learning. With the optimized design and control solution, we then employ a teacher-student distillation scheme to transfer to reality. We roll out the privileged teacher policy to collect expert trajectories, which we use to train a student 3D diffusion policy. The student policy relies purely on point clouds and proprioception, so we can apply it in real world. Okay, so we first evaluated our framework in simulation, shown as the blue bars here. Our co-design method consistently outperforms standard parallel geogrippers, Bayesian optimization, and end-to-end RL baselines. On bulky objects like large jelly cubes, our co-design solution yields a 33% increase in success rate and 36% reduction in maximum induced stress compared to a standard parallel geogripper. And finally, we put the optimization results in real, and shown here are grasping, pushing, and scooping with the optimized solution. In summary, we present the first co-design framework explicitly targeting deformed and fragile object manipulation. Our limitation mainly lies in the fact that we require a set of manual designs for dimensionality reduction and designing motion primitives for model-based control. The future goal is to make the pipeline free of human labor as much as possible. Thank you.
Thanks, Kay. Our next talk will be by Jinxiang Wang, speaking about computational design of a low visibility UAV using a human-aligned perceptual metric.
Hi, I'm Jinxiang Wang, and on behalf of my co-authors, I'll be presenting our work on this invisible drone we name as the Phantom Twist. So on the left, you show the drone static, and on the right is how it looks like when it's flying. So in tasks like human-robot interaction or inspection, like just the presence of the robot itself will have influence on nearby observers. So people have tried to reduce the perceptibility of these drones using either active coloration or biomimicry, but very few tried motion blur. So you can see here, a human eye can be really hard to track a fast-moving object, like a spinning propeller effectively just disappears. We've been working with these kind of single-motor drones. As they fly, they will spin around their first principal axis due to the reaction torque from the motor. So on the right, you can see that when it's flying, some part of its body will look transparent, and we want to create an optimization pipeline to further reduce its visibility. So just like a regular drone, our drone consists of the battery, which provides power, PCB for control, and motor and propeller to generate the thrust to keep them flying. We also allow adding counterweight to balance out the mass. Together, we can parameterize this drone using position, weight, as well as attitude of these components, totaling up to 31 parameters. And as you can imagine, its stable flight really depends critically on these 31 parameters. And so to ensure that they can fly, we use our previous experience to generate 10 constraints in 3 main categories. The mass and inertia constraints that ensure the stability of spin of the drone, control and aerodynamic constraints that ensure that we can control the drone and maneuver in space, and geometric constraints that ensures the feasibility of manufacturing. So once we have a drone, how we quantify the visibility? We use LPIPs, or learned perceptual image patch similarity, to quantify the difference between, like how visible the drone is. LPIPs compute distance between deep neural network activations to represent difference between images and has been shown to closely match human perception. So given a drone configuration, we first turn it into monochrome and then spin it up to generate its motion blurred appearance in flight. We then overlay this image onto a background to generate its appearance in a real-life environment. So we compute LPIP score between the background and the composite image to represent how visible our drone is. In reality, we compute this LPIP score over 100 backgrounds as well as 10 perspectives and use weight average of these numbers to represent how visible our drone is. The lower the metric, the better. In the optimization process, we start with random samples, then use our previously mentioned constraints to filter down only to the valid ones. Then we run a constraint gradient descent using LPIP scores as objective to further reduce their visibility. So as you can see here, these are the 20,000 valid samples that we initially generated, and we optimized the top 500 as shown in the blue. This is a human design baseline and the best results before and after the optimization steps. In comparison, they are 10 times less visible comparing to conventional quadcopter or helicopters. So we built the three mentioned designs, and here's how they look like on a white background flying. As you can see, the human design baseline is more visible comparing to the low visibility optimized one. And here is them on the more realistic background. On the left is a static phantom twist. On the right is a quadcopter. In the middle, it's really hard to see, but it's actually flying, our drone flying in the air. It's just, yeah, you can't see it. And here is them on more like various backgrounds. So while this work can still be improved by modeling all components, using lower visibility components, or using quieter propulsions, because hell, they are still noisy. Phantom Twist shows a new way of using motion blur to achieve low visibility drones and show the pipeline to optimize them. Can you see the drone here? Can't see it? Well, you can see it. We have the drone actually at the poster session, so welcome. Thanks.
Thank you, Jinxian. Our next speaker is Duanpeng Shi. He will present a dual-mode electrical capacitance tomography sensor for robotic proximeter soldering and grasping.
So, my name is Duanpeng, and today I will present our work, an ECT-based sensor approach for robotic proximity sensing. In robotic manipulation, perception is usually divided into vision and tactile sensing. Vision suffers from occlusions and depth uncertainty at close range, while tactile sensing only works after contact. So there exists a critical pre-touch perception gap, typically within the range of 0 to 20 centimeters, where robots still lack reliable perception during approach. Recent studies have explored proximity sensing and capacitive servoing. However, achieving a unified framework that can provide both perception and real-time control remains challenging. So this motivates our work. In our work, we designed two complementary ECT sensors. ECT measures the mutual capacitance between electrode pairs as illustrated by the red lines. Different materials produce distinctive capacitance signatures, which can be used for material recognition before contact. The first is for large area proximity monitoring, and the second is integrated on the gripper for the fine pre-touch manipulation. Our characterization experiments demonstrate that the signals are stable and are suitable for real-time closed-loop robotic control. So the key idea of our work is simple. Instead of manually designing features from capacitive signals, we directly learn task-relevant information from raw ECT measurements. When the robot approaches the object, the ECT sensor captures the changes in the surrounding electric field. Our proposed network directly maps these temporal capacitance signals into task-level states, including proximity information, orientation error, and material properties. These predictions are then directly used for the next closed-loop robot behaviors. So here's the overall pipeline. First, we collect temporal mutual capacitance sequences from the two ECT sensor layouts. The signals are processed by the shared physics-aware backbone. The backbone contains mouse-scale temporal convolutions and ASE attention block to extract robust latent representations. The latent features are then passed into three task-specific heads: the proximity estimation, post-alignment, and material classification. Finally, these outputs are connected to safety control, alignment control, and the grasp refinement modules. So next is our experiments. We evaluate our framework through three real-time robotic experiments. First is the proximity servoing for safety control. And second is the angle servoing, where the robot estimates pitch and yaw errors and line is posed before contact. Third, fine grasping, where the robot performs pre-grasp angle adjustments, and material area grasp refinement. These experiments demonstrate that our method is not only an offline perception model, but a complete closed-loop system capable of real-time robotic control. So to include, this work presents an ECT-based framework for proactive pre-touch perception control. The main contribution is that capacitive sensing can bridge the gap between far-field vision and post-contact tactile feedback. These predictions from our design net enable real-time closed-loop robotic behaviors before contact occurs. So thank you for attention. Happy for the poster time.
Thank you, Duan Peng. Our next speaker is Jin-Chen Ruan. He will present a continuum robot modeling with action conditioned flow matching.
Hi, I have a question. This is not the new one. Oh, yeah, this is the new one. Okay. Hi, everyone. I'm Jin-Chen from Columbia University. Today, I will present our work on continuum robot modeling with action-conditioned flow matching. Our goal is to predict the robot's full settled 3D shape directly from motor commands. This is difficult because analytical models are sensitive to tendon routing, friction, hysteresis, and manufacturing variation. Instead of only predicting the tip post, we model the dense geometry of the entire robot body. Here's the overall pipeline. We set motor commands to the robot and collect RGBD observations after it settles. Multiple camera views are fused into a single point cloud. We then train an action-conditioned flow matching model on these paired commands and point clouds. For a new motor command, the model predicts the robot's settled 3D shape. For real-world data collection, we develop a lightweight and configurable 3D printed TDCR platform. The flexible structure backbone is fabricated in one piece. Its compliance mainly comes from the spring elements, while the connecting geometry helps limit lateral shear and encourage controlled bending. We also design removable support structures for single-pass printing. Each module is driven by 3 tendons arranged 120 degrees apart, and 4 calibrated real-sense cameras reconstruct the robot in a shear coordinate frame. During training, each motor command is paired with the target robot point cloud, X1. We assemble a Gaussian point cloud X0 and the flow time T. We then construct an intermediate point cloud between the noise and the target shape. Along the straight interpolation path, the target velocity is simply X1 minus X0. The network receives the intermediate point cloud, the flow time, and the motor command, and learns the corresponding conditional velocity field. The motor condition is injected through film layers. At prediction time, we only provide a new motor command. Starting from Gaussian noise, we integrate the learned velocity field from t equals 0 to t equals 1 and generate the settled robot shape. Flow time is only a generative transport variable. It's not the physical deformation time of the robot. Here, the left side shows our prediction. The right side shows the simulation ground truth. We first show the 2-module robot, followed by 3-module and 5-module robot. As the robot becomes longer and the shape space becomes more complex, the model still captures the main bending direction, the tip location, and the overall body geometry. Here we show prediction for physical 2- and 3-module robots. Across different motor commands, the model generates coherent and settled shapes. Each pose is a quasi-static prediction for a command state rather than continuous dynamic tracking. Here we compare against point flow, visual self-modeling, a nerve-based method, and 3D Gaussian splatting. Across simulation and real hardware, our predictions remains closer to reference geometry, especially for longer and more complex multi-module robots. Finally, as a supplementary experiment, we test whether the same framework can learn an effect of a gravity-aligned tip load on the TDCR shape. We add the payload magnitude to the motor condition. Blue indicates unloaded and red indicates loaded. The predictions capture the load-induced deformation across 2, 3, and 5-module robots. They are all in simulation. And thank you for listening. Here's the QR code for our project website. Please feel free to visit our poster for further discussion. We also brought the physical TDCR robot, so you are very welcome to come and try it out. Thank you.
Thank you, Jin-Chen. Our next speaker is Gaofeng Li, and he will present a super resolution and multi-axis tactile sensor with soft artificial skin.
Okay, thank you. Hello, everyone. My name is Gaofeng Li. I'm currently a tenure-track assistant professor from Zhejiang University. Today, I will present our work super resolution and multi-axis tactile sensor with soft artificial skins. Tactile sensing is essential for robotic manipulations because it can provide local contact information that vision cannot replace. However, existing solutions takes a trade-off. The vision-based tactile sensor can achieve high resolution, but abruptly are hard to achieve miniaturize. And the electronic skin is scalable, but high resolution needs dense array, complex whirling, and high cost. So our insights come from our human skins, and the force spreads through our soft skin and excites multiple receptors simultaneously. So this coupling effect can provide more information beyond the physical sensing spacing. So following this idea, we add a soft silicon layer on the top of the sensing area to simulate the soft tissues in our human skin by using its coupling effect to achieve super resolution. But in previous work, the super resolution sensing is still limited only in the normal force. So in this paper, we designed a tiny 3D force sensing unit to stimulate the microreceptor in our human skin. And then this sensing unit is embedded into a soft layer to achieve multi-axis super resolution sensing. The final performance is summarized. And our method has two levels. First, its sensing unit uses 3 Kelly levels with string gauge. And the finite element analysis shows that different directions will produce different deformation patterns. So it is possible to decouple the 3D force. So for the near normal loading, we will use the model-based way to calibrate it. And for the large angle loading, a neural network it will be used to capture its nonlinear effect. And second, in the upper level, we will arrange the 4 units to be covered by a soft skin. And the decoupled force are sent to a neural network to estimate the external 3D force and contact location. Here are some examples by using our tactile sensors. On the left, a single sensing unit is used as a 3D joystick. So the sensed force can command the robot motion along X, Y, and Z to allowing the insertion of a test tube into a racket hole. And on the right, the tactile sensor can enable adaptive grasping. When the disturbance increases along the gravity direction, the gripper will increase the normal force to prevent slip. But when the horizontal pull is detected, it can recognize the retrieval intention and release the ball. So we provide another demonstration here. On the left, except for the contact position, and our sensor can also estimate the shear direction. So together with 9 grids and 4 directions, our sensor can be served as a high-resolution keyboard to provide 36 inputs. And in the right, and the user is allowed to draw a digital on our sensor surface. Our sensor can capture its contact trajectory smoothly in real time, and we send this trajectory to CNA to recognize it correctly. And this is all. In summary, we provide a tactile sensor which is able to provide multi-axis super resolution sensing by using the coupling effect of our soft tissues. Welcome to stop by our posters and for more discussion. Thank you.
Thank you, Gaofeng. And our last speaker is Ziyi Zheng. He will present the active surface-driven reconfigurable gripper, which is robust for grasping and sequential manipulation of thin objects.
Yeah. Good afternoon, everyone. I'm Ziyi Zheng. Today, I will introduce our work on active surface-driven reconfigurable gripper for grasping thin deformable objects. Grasping thin deformable objects remains challenging because these objects are usually very thin and easily deformed during manipulation. Many previous studies have used finger gating to maintain force closure during the grasping process. However, this often introduces a relatively complex control strategy. Therefore, our key question is, how can we design a gripper that can grasp thin deformable objects with relatively simple control? In this work, we focus mainly on box as target objects. This is because books not only exhibit typical deformability as thin objects, but also consist of separable layers, which makes the grasping process even more challenging. Considering two common cases, books lying flat on a table and books arranged on a shelf, we define the main target. First, the gripper should be able to effectively separate a book from the tabletop without causing the interlayer separation. And the second is it should be able to remove a book from a shelf without disturbing the surrounding books. In addition, the gripper should have simple control logic and be able to switch between these two cases. To achieve these goals, we developed an active surface-driven reconfigurable gripper. First, we propose a novel gripper that integrates an active surface structure, reconfigurable mechanisms, and under-attached joints. The gripper has 3 motors in total. One motor drives the belt of the active surface, and the other 2 motors control the coupled opening closing motion and the coupled reconfiguration motion of the 2 fingers through gear mechanisms. With this design, the gripper can adapt its configuration to different grasping cases while keeping the actuation system relatively simple. Second, we propose an active surface-based grasping strategy. Instead of relying on complex finger gating during grasping, the gripper only needs to determine the initial configuration. Then, the active surface is used to reposition the thin deformable object and guide it into a stable grasping state. Third, based on the Bayes theory, we analyze the contact conditions during the grasping process. These analyses help us understand how the thin deformable objects bends and interacts with the finger during manipulation. Based on the results, we further optimize the structural parameters of the gripper and refine the grasping strategy. Based on the proposed grasping strategy, we conduct grasping experiments on books in 2 different cases. The first case is grasping books lying flat on a table, and the second case is removing books from a shelf. Thanks to the repositioning capability of the active surface, the grasping process shows good stability in both cases. The proposed gripper can also stably grasp extremely thin objects placed on the tabletop. We tested several representative objects, including plastic sheets, fabric, ace paper, and mouse pad. Finally, we also conduct grasp and place experiments between a table and a shelf. Especially, we test both table-to-shelf and shelf-to-table manipulation tasks. During both grasping and placing, the active surface is used to reposition the book, which reduces the complexity of the control process. Thanks for your attention.
Thank you, Ziyi. Now welcome our other speakers, and now come to the Q&A session. So if you have any questions, please feel free to reach out to the microphone.
We've got about 5 minutes for questions, so take advantage of this opportunity. While folks are getting up to the microphone, I'll ask one question. For the hybrid hard-soft compliance tendon-driven hand, I'm curious if you've explored multi-material printing to put together the hard and soft parts, or if you assemble them after the fact from different, different prints.
Okay, so for like multi-printing, we have not experimented that yet because it's gonna like increase print time, which is gonna like waste time. So currently we like separately print the TPU and the PLA like separately. So we can try that out, but currently like our structure, like we have to print it flat, and then like we have to like curl it up a little, and then like we have to, yeah.
So there's some challenges.
Yeah, it's a challenge, yeah.
Yeah, thanks. Looking to see, we've got one right in the back over there. Let's start with the orange mic in the back right there.
I have a question for the author of the disappearing drone paper.
Do you have any thoughts on how you might be able to make it also silent eventually, like toroidal props or something like that?
Oh yeah, first, because we're academia, so we can't gain access to the best kind of motors and propellers, so they can definitely get quieter on that side. But generally speaking, there are electrostatic propulsion methods, and they can also be implemented on such drones. Well, we don't know exactly how to do that yet, but I think there are also other types of these single motor drones that can work with those propellers, and those are basically silent. So yeah, there might be solutions to it, but yeah, it's going to be hard.
Cool. Very cool. Thank you. Let's go down in the front right here.
Hi, I also have a question for the same paper. I'm right here.
Oh, hi.
Yes. I wonder, when you first started this project, what use cases did you have in mind for your stealth drone?
So this project is actually a kind of a side project for our main project, which is also single propeller drones. We kind of explored multiple directions. We can chat at the poster session. But for this, I'll say it's just for fun, honestly. My advisor will not be happy about this, but this is just a for fun project.
Yeah. Let's head to the fixed mic right here.
This is a question for the visual touch sensing paper. I was wondering, have you looked at whether it's possible to also incorporate something like gel sight, so you get the touch map and a bit of a pressure map at the same time?
So can I repeat your problem is that compared with the gel sight sensor, what's our benefits? Is that your problem?
Like the gel sight gives a bit of a pressure map, whereas
yeah.
Does the gentle touch. Have you looked at whether you could combine the two with different?
Evaluate the comparison with some?
Yeah.
Okay, so thank you for your problem. And here is that we want to better to demonstrate our motivation. Is that we appreciate that the sensor, vision-based tactile sensor, for example, the GeoSat, they achieve a very high resolution perception. And this is a very good thing. And also they have rich texture sensing. So I appreciate that work. But the visual-based sensor, they meet a bottleneck, which is that they have to leave some space for the CMOS components and to leave space for the foxing. So it is difficult to achieve to make it to be singing. And also it is difficult to deploy it at a very large area. So I admit that our sensor, its performance cannot compare with the tactile the vision-based sensor. But we want to achieve the performance which is similar to that solution, but we have the potential to achieve seeing and large area sensing. So that is our idea. Okay. Thank you for your problem.
If it's a real quick question, we can do it. We've got about 30 seconds left. Go ahead.
Yeah, sure. I have a quick question for Light Tech. I think it's really cool work, and I wonder if it's already open sourced, or are you planning to do it, like for yourself?
Yeah, I have open source almost everything. So.
Okay, cool. Yeah. Thank you.
Great. All right, let's give one more round of applause for our speakers here. Thanks, guys.
Okay, welcome everyone to the last session, imitation learning. So I'm Yunzhu Li from Columbia.
I'm Vince Kurtz from DePaul University.
So without further ado, let's start with the first presentation. Unfortunately, the speaker won't be able to come here to do the presentation in person. So we'll be playing a video on long context robot imitation learning by focusing on key history frames.
In this video, we will present our project Long Context Robot Imitation Learning by focusing on key history frames.
Can we have the audio?
Most of today's robot policies are memoryless. They choose actions using only what they can see right now. That works for some tasks, but it breaks down as soon as the task requires remembering what has happened earlier. For example, imagine searching for an object in a set of drawers. To search efficiently, the robot has to remember which drawers it has already checked. So we may ask, why not just give the policy more of the past, a longer observation history, and just call it a day? Consistent with prior work, we find that naively conditioning on long histories doesn't help much, and in fact, in some cases, it actually makes performance worse. When we dig into why, we find a key issue. Policies trained on long histories tend to latch onto spurious correlations. More specifically, these policies can correctly infer the task's history states on unseen expert trajectories, which still look like the training data. But on the policy's own rollouts, which drift out of distribution, that history understanding deteriorates sharply. To address this, we propose a simple approach called Big Picture Policies, or BPP. The key idea is the following. Instead of conditioning on a long stream of observations, we condition on just a few salient events, a small set of keyframes that are still sufficient to solve the task. To find those keyframes, we use an off-the-shelf vision language model to detect behaviorally meaningful events. For example, the object has been grasped or a drawer has been opened. By collapsing messy, diverse trajectories into compact sequences of task-relevant milestones, BPP substantially reduces the distribution shift between training and deployment. We evaluate BPP on 4 challenging real-world tasks and 3 simulation tasks. Overall, in the real world, BPP achieves up to 70% higher success rate than the strongest prior history condition baseline. The drawer search task is a long horizon search task in which the robot has to look for a hidden key among 6 drawers. In the stacking puzzle task, there are 3 pieces of different colors stacked in the middle of a table, and the task is to put each piece with their respective color on the right, and then stack them back in the middle in the original order. The mug replacement task is simply to switch which mug is in the coffee machine. Finally, the marshmallow insertion task requires the robot to insert 2 handfuls of marshmallows and then press the red button. The key takeaway is that for long horizon history conditioned robot learning, the big picture is what matters. By focusing on semantically meaningful milestones instead of raw history, we get policies that are more robust, more data efficient, and better at long multi-stage tasks.
All right, our next speaker will be Uksang Yu, talking about functional force-aware retargeting from virtual human demos to soft robot policies.
All right, hi, I'm Uksang, and I'll present our work, Soft Act. As you saw from today's or this year's Test of Time awardee, soft robot hands offer passive compliance that can make them more robust. Prior imitation learning works let soft hands leverage this unique morphology, but they rely on expensive embodiment-specific data sets. Learning from human demonstrations directly instead leverage a scalable data source, but existing retargeting algorithms often assume anthropomorphic hands or fixed finger-to-finger mappings. So our question is, how can non-anthropomorphic hands learn directly from human demonstrations? And our key idea is that retargeting contact forces, not just poses, is what can bridge this embodiment gap. And that VR with physics simulation lets us capture those privileged contact demonstrations. And let's see the target hand design first. Each finger has 3 parallel pneumatic chambers, so differential pressure can bend them. And combining 4 of these fingers gives us a dexterous, non-anthropomorphic soft hand mounted on a robot arm. And because pressure causes nonlinear deformation rather than joint motion, we build a soft body simulation of the hand. We approximate pneumatic actuation with internal torques on a rigid spine inside each of the fingers and compose a full hand in simulation. Next, we collect human demonstrations with privileged contact information. A demonstrator performs each task in VR environments. We track the hand with motion capture and record hand poses, object motion, contact locations, and force vectors. We collect demonstrations for 6 contact-rich manipulation tasks, from cup pouring to bottle unscrewing. And we do this with variations in trajectories, contact placement, force distribution, as you can see here. Now we'll move to retargeting. Kinematic retargeting often assigns the robot fingers to finger of the humans and track positions, ignoring which contacts actually matter. And under severe embodiment mismatch, this produces poor results, leading to task failure. SoftAct instead uses demonstrated forces. In stage 1, we diffuse the demonstrated forces, then allocate the fingers based on the contact load. In the stage 2, each of the contacts pull the nearby robot fingertips with force-weighted influence and refine the match contact. The resulting motion can look a little bit different from the humans, but it better preserves the demonstrated contact functions as shown here. Across tasks, the robot can discover the strategies better suited for its own embodiment, rather than mimicking human poses poorly and leverage the force information. From these retargeted trajectories, we can train a behavior cloning policies for all 6 tasks. And finally, to execute these policies, we have to transfer the kinematic actions from simulation to physical pneumatically actuated hands. Pressure and contact finger poses are non-linearly related, so we train a inverse model that maps from desired fingertip poses to chamber pressures, and this cuts our tracking error than the baseline controllers. And at the policy level, SoftAct consistently outperforms the kinematic baselines in simulation and in zero-shot real-world deployment. For example, 70% versus 10% success on box reorienting. And the gains are largest where we have to maintain these contact conditions very well. Now, to conclude, contact force data can be captured in VR demonstrations with the physics simulation. SoftAct uses those contact forces for force-aware retargeting across embodiment gaps. And the learned low-level controller enables a real-world deployment of these policies to the real-world soft robot hands. And the main limitation still is that the deployed policies actually has no tactile feedback, and closing that loop is an exciting future direction for our work. Thank you so much for today, and I look forward to your questions either here or at the poster session later.
Our next speaker will be Lihan Zha. He will be presenting us lab language action pre-tuning enables zero-shot coarse embodiment transfer.
Hi everyone, this is Lihan, and I'm here to present lab. General pre-training recipe for vision language action models that enables zero-shot cross-embodiment transfer. So the ultimate goal of a robot foundation policy is to perform human-level tasks on any robot. However, as shown in these videos, so for a lot of like state-of-the-art VLAs, for example, Pi 0.5, so they actually completely fail on some new on-scene embodiments. So even if they are pre-trained on massive multi-embodiment data sets. So this raises the central question, why do these VLAs fail to generalize to new embodiments zero-shot? So our key hypothesis is that adapting VLMs to VLAs introduces action implementation misalignment. Actions correspond to high-frequency control, a modality that VLMs have never seen during pre-training. As a result, introducing actions creates a distribution mismatch that can degrade the model's pre-trained vision language knowledge. To address this, we adopt a very straightforward yet effective solution, representing actions as language. We parse and factor delta posts into directional movement descriptions, for example, move forward, tilt left, open gripper. This action implementation aligns better with VLM's pre-training distribution. To avoid slow autoregressive generation and inaccurate control, we adopt a mixture of transformer architecture, where a lightweight flow matching action aspect runs at 25 Hz during inference time. And language action prediction is only used as an auxiliary training loss to help the VLM to learn better representation. To summarize, we propose language action pre-training, a method that enables vision language action models to learn transferable features across embodiments. We demonstrate that lab leads to the first VLA that can achieve substantial zero-shot generalization to on-scene embodiments when trained only on an open-nest embodiment dataset. So we believe this also highlights the strong potential of scaling this approach to more diverse and larger datasets. So we evaluate lab across a wide range of tasks on on-scene embodiments, demonstrating very strong motion level and also task level transfer to new robots. For rigorous valuation, we compare against both existing open source VLAs and our replicated baselines. Notably, we show lab can achieve 2 times performance compared to Pi 0.5 replicated over multiple on-scene embodiments. On the other hand, Pi 0.5 replicated, which only differs in that it uses fast tokens instead of language actions, completely doesn't work very well. So this is a more like demo showing the Bose policy on a new robot, which is YAM. It's not in the training distribution. So as you can see, our model can have the ability to recover and successfully finish the task, but the baseline will attempt to grasp the tissue box instead of the tissue so as to fail the task. So we also show that lab can be efficiently adapted to new embodiments on challenging tasks. So lab can achieve the same success rate with 2.5 fewer demonstrations, demonstrating that language action pre-training provides a strong initialization for data-efficient post-training. So next, we are going to talk about why does lab work surprisingly well. We believe the answer is all lies in the learned representations. So on the left figure, we visualize the representation space learned by lab and Pi 0.5 across scene and on-scene embodiments. For lab, the on-scene embodiments overlap closely with the scene ones. In contrast, Pi 0.5 forms more separated clusters. On the right, we show that this is actually an interesting thing. Like we show on some on-scene embodiments, not on held-out scene embodiment validation set. Our model can learn a more monotonically decreasing and smooth curve, which demonstrates the learner recitation is actually generalizable, but not an artifact of some optimization. So please scan the QR code and visit our poster for more details. Thank you very much.
Thank you. Okay, our next speaker will be Modi Shi, talking about unlocking in the wild local manipulation with robot-free egocentric demonstration.
Hello everyone, I'm Modi. I'm here to present Ego Humanoid, teaching a humanoid local manipulation from in the wild human videos. I'll begin my presentation with a funny questionnaire from Haoru. Which task is harder for a humanoid, Kung Fu or opening a door? It really depends on who you ask. The general public and even most large model researchers think Kung Fu is harder, but robotics folks say the opposite. It's a door, the everyday local manipulation task. That's generally the hard part. Previous work usually handles the 2 pieces separately, by manual manipulation on a fixed base, and the humanoid locomotion on its own. But real tasks need both at the same time, and we think we should do them together. That's local manipulation. Now, the obvious approach is to do what manual manipulation does, just collect a ton of robot teleoperation data. The problem is that that's expensive, operationally complex, and stuck in the lab. So it really doesn't scale. Human data is a great alternative. People already do this task every day, everywhere, so it's cheap, portable, and diverse. And can we just use existing human data sets? Unfortunately, no. There are plenty of egocentric data sets, but none of them have whole body pose, which is exactly what a humanoid needs. And that's ego humanoid. We co-train a single VLA policy on a big pile of cheap human data that has whole body pose, together with a small amount of robot data. The human data brings the diversity and scalability, and the robot data anchors it to the robot's body. We use a Pico headset with body trackers to capture human demonstrations with full whole body pose, anywhere, no robot needed. Here are some examples of the data. With the robot, we collect 4 tasks in the lab: card stowing, toy transfer, trash disposal, and pillow placement. And the same 4 tasks as human data, but now in the wild. This is where the scalability and diversity come from. Real stores, homes, and outdoor scenes, all collected without any robot. Now, there is still the embodiment gap between human and robot data. They differ in viewpoint and in how actions are represented. So before co-training, we align them. View alignment reprojects the human first-person view to what the robot will see, and action alignment maps both into one shared action space. So we co-train on everything. And it works. Aiding the human data clearly improves the robot's performance, especially in environments it never saw during training, where co-training gives a 51% boost. Cheap human data rarely does bad. Really, that's by real-world generalization. And the best demonstration of that, thanks to the human data co-training, the policy transfers cell shot to completely new environment out in the wild. On a waterfront in Shenzhen, doing trash disposal. We never collected any data here. It just works. We also find this is a scalable recipe. Performance keeps improving as we add more human data. And the best human-robot ratio depends on how precious the task is. Cheap data, scalable skills. Zooming out, we put eco-human node alongside prior work that use human data for co-training. The big picture and our future work is to keep scaling egocentric human data and push towards more dexterous generalist human nodes. And it's all open. The training code and sample data are on GitHub, so please grab them. That's all, thanks. If you have any question, come find me at the poster. Thank you.
Our next speaker is Jeanette Bao. She will be presenting to us Homie, learning whole body mobile manipulation from human demonstrations. Please.
Thank you. Hi, everyone. I present Homie, the whole body mobile manipulation interface. So let's first look at what our robot can actually do. So here you see it traversing a large workspace and transporting a box to a trolley. And here you see it coordinating its two hands and whole body motion to get to the table and fold this mat and put it flat onto the table. And finally, here you see it grasp a piece of laundry and then actively search for the laundry hamper to actually put it in. So the important thing is we enabled all these capabilities without any teleoperation data. Instead, we learned directly from human demonstrations that we collected with the scalable data collection interface. Basically, it's two Yumi grippers and an egocentric camera, and that camera provides an egocentric view, which provides the context that is important for mobile manipulation. But we also get a huge human-to-robot embodiment gap. So there is the kinematic gap, first of all, which comes from the camera of the robot being lower than the one from the human, and the neck actually also only has 2 degrees of freedom. And then we have a visual gap that stems from the different viewpoint, and also the embodiment actually being in the frame as well. So the key question is, how do we bridge this embodiment gap? So what we do is, to bridge the visual gap is to first lift everything into a 3D embodiment agnostic observation. And then also we represent everything relative to an embodiment agnostic gripper coordinate frame that also makes it easy to mask out the embodiment specific information in that frame. And to bridge the visual gap, we actually or the kinematic gap, we actually represent the gaze at the lookout point, and then we let the demonstrator and the robot look at the same lookout point from a different height. And together, these two solutions give us an embodiment agnostic policy. But how do we actually execute this policy now on the robot? For that, we need a policy that respects the constraint on the actual robot. And we developed a whole body IK that takes bimanual end effector poses as input and the current robot state and then produces joint velocities. The lookout point actually lets us decouple the control of the head and the control of the end effector, while trying to track everything at the same time leads to large tracking error. We also include a bunch of constraints to make the robot stable and robust and safe, as you see here. And now we finally arrive at Homie, where we co-designed the data collection interface, the policy representation, and the controller to learn directly from human demos. So let's look at more results. So here you have a comparison between a wrist-only policy and ours, and you see that the wrist-only policy will actually not find the hamper because it doesn't have the global context and will put the laundry to the wrong side. Here you see a head-only camera, and that one struggles with actually grasping correctly because it doesn't have all this information about contact and so on. If we were to naively add the RGB frame and regress directly 6 head poses, that leads to really poor performance of the policy. And finally, if we disable the active neck control, that typically leads to poor alignment between the robot and the final target. So mobile manipulation is hard because for all these reasons on the slide, it leads to higher control complexity and larger action and observation spaces. And we showed with Homey that if you co-design the data collection interface, the policy and the control, we can actually directly learn from these human demonstrations. So if you want to know more, please come to the poster. Thank you, everyone.
Thank you. Our next speaker is Renming Huang, talking about mimic intent, not just trajectories.
Hi everyone, I'm Renming. I'm here to present mimic intent, not just trajectories. Imitation learning has achieved great success in distribution setting, but when facing out-of-diffusion disturbance, like a shifted object, the policy often fails to generalize. This is because models try too hard to mimic the raw shape of trajectory, but the underlying intent remains consistent. To succeed, the model simply needs to mimic the intent and convert it into executable action. Therefore, we agree that the model should understand the intent, not mimic the raw shape of trajectory. But how can a model understand the underlying intent? Here, we introduce the spectrally disentangled action tokenizer. The tokenizer encodes action chunk into latent embedding. Then it performs the multi-scale quantization to generate a pyramid of discrete tokens. The tokenizer is trained to progressively reconstruct the frequency domain spectrum, which convert from the time domain signal using DCT. And additional time domain reconstruction are used as auxiliary loss. This one token captures the global shape of trajectories, referred to as intent token. The final token contributes motion details. We call them execution token. We visualize the intent token space and observe a strong correlation between intent token and behavior semantic. We reuse the tokenizer to train our policy. Giving vision and language input, the model generates intent token first. Then it predicts execution token scale by scale. This performs intent to execution reasoning. And the sequence of tokens are decoded into trajectory. During training, giving an expert demonstration, we first convert it into execution and intent token, and then mimicking the behavior intent and execution logic. We show that mean to achieve state-of-the-art performance across diverse public benchmarks, outperforming the best models. It's particularly strong in generalization, with train means on liberal and evaluate on liberal plus, which contains a variety of perturbations. Means still demonstrates strong, robust performance, outperforming the representative baseline across all types of perturbation. In real-world experiments, we roll my means on bridge datasets and fine-tuning on 3 tasks, each with only 20 demonstrations. Means successfully comprehended these skills and was able to transfer the stacking skill from stack blocks to unseen task stack caps. Intent tokens are much more powerful than we thought. It opens up a new way for one-shot transfer. Given just a single demonstration, we use the tokenizer to extract its intent and execution tokens. For a new environment, we simply inject the intent token into Mint policy. Mint predicts the execution tokens autoregressively, which produce a decoded trajectory that adapts to the new environment. We also show that the one-shot capability can across the novel task, unseen layout, and compositional task. And the result is awesome. Here are takeaways. First, intent and execution token and execution details can be disentangled. And intent to execution reasoning can boost the generation, and intent injection offers an approach for one-shot transfer. Thank you for listening, and please visit our homepage for more details.
Next, we have Riyad Ahmed to presenting to us TailSafe, task-agnostic safety monitoring for imitation learning policies.
Hello, everyone. I'm Riyad Ahmed. I'm going to present my paper, TailSafe. In typical imitation learning policy, we provide a robot with the task demonstrations, and then we train the policy out of it and let it run. This policy takes an observation as an input and predict the next action. But here's the core ratios. Naturally, this kind of policy rollout gives us two types of outcome. Either it's successful or it's failed. But the issue is that policy itself acts as a black box. We have no way of knowing when the robot is going to be succeeded and when it's going to be failed. This unpredictability is a massive problem because real-world failure causes serious and costly damages. To build a reliable safety monitoring system, we need to anticipate a failure before it actually happens. To do this, we need to collect failure data, and it's very difficult to collect failure data in real robot settings. Instead, what if we have a photorealistic simulator? So we build a high-fidelity digital twin. This will give us a safe sandbox where we can run our real robot policy and see when the policy is actually failing and when it's actually succeeding. We build this system first by collecting a set of images of the real-world setup. We then fed these images to Dino and Sam to extract a handful of features, which we then use to reconstruct a 3D Gaussian splatting environment where we can run our policy rollout and see the policy behavior. With this highly accurate digital twin in our hands, we can now safely deploy our policy and explore its operational boundaries and pin down the exact policy failures. Once we track these trajectories in the simulator, we calculate a Q-value function out of it. And this Q-value function has a reward value, which is basically a weighted sum of three modular score. One is recognizability, second one is the visibility, and graspability. Crucially, this value is not static. It dynamically adapts along the trajectory, prioritizing which modular score needs to be given more priority in a given state. However, standard Q-value function is discontinuous and lacks a proper gradient toward the safe set. So, without a clear gradient, a neighboring state along a trajectory cannot give the robot proper recovery from an unsafe state to a safe state. To fix this, instead of using a raw Q-value function, we apply two critical constraints in the training. First one is the least discontinuity, second one is the energy shaping. So without this constraint, the gradient looks flat and completely failing to guide the robots back to the safety. But when we enforce this continuity, least discontinuity and energy shaping, we can see that the entire state space transforms and creating a smooth and well-behaved gradient toward the safety. We validated our system in Gaussian splitting simulator, and you will see that the Q-value function recovery accurately keeps the robot within the safe set from start to the end. We then tested this recovery method in the real robot. Here you will see that the operator will manually disrupt the robot when the robot is executing a task. And as it has the learned recovery method in it, every time the operator interrupts the robot, it will safely return back to the safe set again and again. Even when you will physically push the robot very hard out of the safe set, it will not crash. It will come back to the safe set and maintain the recovery throughout the process. So ultimately, these frameworks provide you a robust safety monitoring system without risking any hardware damage. Thank you so much.
Thank you. Our next speaker is Matthew Hong, talking about diffusion time-step modulated pre-training.
Hi, I'm Matthew, and I'll be presenting our work. TMRO, Diffusion Time-Step Modulated Pre-Training, enables acceleration for efficient policy fine-tuning. VLAs like Pi0 have shown impressive generalization capabilities. Yet when we asked it to pick up the sausage here, it reaches for the carrot instead. Looking closely at the data, we found that it was full of carrots and the policy had learned to overfit to them. We want to fix this with RL, but if the policy never stumbles into any successes, RL has nothing to reinforce. Here, we can take a further analysis why this failure happens in a simple point-made setting. We visualize action samples from a BC policy on an unseen goal and see that the actions drifted further away from the goal. Then, we plot the marginal action distribution and see that its distribution is much broader and actually covers the goal, just under low probability. So neither extreme works, since BC is precise but collapsed, but the marginal is broad but unfocused. So this begs the question, if BC ties each input to a narrow behavior mode, how can we broaden it for RL? Our key insight is that rather than relying on only the conditional or only the marginal, we learn the whole spectrum of action distributions between them. How do we do this? By adding noise to the policy's inputs. When humans squint at unfamiliar objects, we are still able to see its rough shape. And in the same way, by adding noise, our policy is able to alias unfamiliar objects onto ones that it has already seen. Our method is extremely simple to implement on top of existing VLA pre-training pipelines. Concretely, standard VLA pre-training conditions the action expert on a clean context. Using context-smooth pre-training, we insert a corruption kernel that is exactly the forward process of a diffusion scheduler before sending the context to the action expert and train our VLA across all noise levels. This gives us a single policy that represents a spectrum from precise conditional to the broad marginal. Then to leverage the spectrum, TMRO freezes the VLA and trains a lightweight high-level policy, which picks the smoothing level per time step to maximize a downstream reward. This turns the smoothing level into an exploration knob, which can be dialed up to explore and back down to sharpen for precise execution. We evaluate TMRO across 8 tasks that span simulation and the real world. So before any RL, we show that context smoothing already widens the policy's coverage, and most notably on this cube single task, both pre-training baselines are unable to succeed at the task. And then we show that this coverage translates into more sample-efficient RL, where we match or beat every baseline across 4 tasks. On the hardest task, we're the only method to succeed non-trivially. And then finally, we show that our method can be applied to the real world, where we perform real-world reinforcement learning on a Pi0 VLA, and show that we can outperform the base model trained with DSRL. Finally, here's a run of TMRO on one of our tasks live, starting from near zero successes and we're able to learn this task to perfect success rates in about 45 minutes of on-robot time. So here are some takeaways from our project. We pre-train policies for RL fine-tuning rather than simply imitating the demonstrations. Context smoothing aliases context, so the policy is able to borrow coherent actions from nearby contexts, gaining the coverage that RL needs. And TMRL learns how much to smooth during reinforcement learning. And our method applies to any policy input, for example, states, point clouds, or VLM embeddings. For more information, please check out our website at the QR code above, and come find us at the poster. Thank you.
Next, we'll be hearing from Jingdou Jia on action-to-action flow matching.
Hello, everyone. My name is Jingdou Jia, and I come from NTU Math Lab. And today is my pleasure to share our synth work, a very simple yet effective robot policy, action-to-action flow matching. For robot learning, recent years had witnessed a great success of generative-based policies, such as diffusion policy and flow policies. And by framing the robot learning as a conditional generative process, this method can capture complex, especially multimodal distributions. However, the real-world deployments are hindered by a one-node limitation, the denoising from scratch paradigm. Under such paradigm, each clean action needed to denoise from pure Gaussian nodes. That usually need dozens of interactive steps. However, it's usually computationally slow, and it's really hard to be deployed in real tasks, especially for some tasks that require fast reactive ability. And here is our question. Can we generate the action without the noise? And actually, the diffusion policy and the flow matching schemes are also from the conventional vision field, all right? However, the robot control operates some very fundamentally different region because we can get some state fact and to infer its history actions. So we're wondering if we just replace its Gaussian noise with its history action, because the history action distribution will be more closer to its future action, all right? So maybe we can fewer inference steps to get a very good action. And so that's the key set of our proposed action-to-action flow matching, I'm showing you the figure. And this slide details our architecture, and the key thing is the training loss. Apart from a standard flow loss, and the autoencoder loss is responsible for the encoder and the decoder, while the consistent loss tries to learn the action inferred with its ground truth in both latent space and the original action space. And we test it across five simulation tasks and 2 real-world tasks. And we also compared it with 8 SOTA baselines, including diffusion policy, flow matching, and their variants. And first, let's see its training efficiency. And we can see that action-to-action flow matching can converge faster than the diffusion policy and the flow matching. And if we give a fewer demonstrations, we also can see the action can also reach its performance settings more fast. And more importantly, what's about its inference speed. And if we increase the number of steps, it will lead to a big improvement as expected. But if we set the inference step and only 1 step, and we found that action-to-action can still reach its performance setting with fewer training upcodes. And the action-to-action maintains around 1 milliseconds, while on the same conditions, the compared diffusion may cost us thousands of milliseconds, which showing its faster inference speed. And we also test its generalizability, which is in the background, lighting, and the camera viewpoint. We found that the action-to-action can maintain a very robust success rate compared to the baseline. And in real-world tests, we try to replace the grasp curve with an unseen glowing block, and we found that the action-to-action can also maintain a very high success rate, where the compared method are totally failed. And this is a team member that involved our project. And more recently, we have made some amazing project that's based on the action-to-action architecture. And welcome everybody to see our lab set. Thank you.
All right, our very final presentation will be on LDA 1B. Take it away.
Hello everyone, today I will present LDA 1B, Scaling Latent Dynamics Action Model via Universal Embodied Data Ingestion. Robot learning is now entering a scaling area, and language models gives us a useful lesson for scaling. Next token prediction turns diverse text across sources, quoted, and domains into one unified training signal. However, embodied data is always heterogeneous. We have expert trajectories, but data collection and policy rollouts also produce many failures, imperfect behavior. Beyond robot data, action-free human videos are much easier to collect from internet and daily recordings. The latter two are hard to integrate into policy learning, but contain rich physical knowledge. So our question is, can we unify them all to scale one model? Our answer is LDA, a word action foundation model combining policy learning and word modeling. LDA jointly trains 4 tasks: policy learning, forward dynamics, inverse dynamics, and visual forecasting. Together, they learn actions, action consequence, and physical knowledge. Based on these objectives, we propose universal embodied data ingestion. Expert trajectories train policy, suboptimal and noisy trajectories train dynamics, and action-free human videos train visual forecasting. So all data can be ingested into LDA and play their own role. At the architecture level, given a task embedding, LDA uses one shared multimodal diffusion transformer backbone to predict action chunks or future visual states, with other set conditioned on the other. One key design is the latent dynamics. Instead of predicting pixels, LDA predicting future representations in structured deno-latent space, avoiding spending capacity on lighting, texture, and color, while focusing on semantics and geometric scene changes. To support scaling, we built Embodied Interaction 30K, a dataset containing over 30,000 hours of human and robot trajectories. We convert them into a common robot-style format and align anti-factor and hand coordinate system across embodiments. Together, this co-design of data, training paradigm, architecture, and latent representations enables LDA to scale effectively. As we add more embodied data, including low-quality trajectories and action-free videos, LDA continues to improve. We also observe model size scaling. As the model becomes larger, latent denote dynamics improve further than pixel-level prediction. In real-world experiments, LDA outperforms strong VLA baselines, including Pi05, across contact-rich, dexterous, and long-horizon manipulation. With only 1 hour of post-training data, LDA adapts to new embodiments, from 2-finger grippers to 3-finger and 5-finger dexterous hands. Beyond embodiment, it also generalizes to unseen objects and variations in appearance, placement, and interaction. LDA can also control a dexterous hand to use tools, completing a stick cooking task with flipping, plating, and seasoning. Not just research, but also application. Across retail, industrial, and household scenarios, LDA is already being applied to real tasks. While continuously observing new streams of embodied data, and our path is clear: keep building and keep scaling. Thank you.